All right, we'll get started. Before I do, is there any questions about anything? All right, seeing none. All right, so we'll continue going through the attack tree that we started last class. And next class, which will be in 2 weeks because of reading week next week, we'll finish the attack tree. Okay, so just remember that an attack tree is all the possible ways of attacking a system, and not only just like not every attack on the system, but what you do is you start with one particular attack on the system. So you want to break one property of the system, you do an attack tree for breaking just that one property. So it's a brainstorm of every attack on one property of one system. So the system that we're illustrating it with is called HTTPS. It's the sort of encrypted version of HTTP, which is the protocol that you use for fetching websites. And we established that the way we're going to go through the attack tree is we're going to look at 3 kind of high-level attacks. So last class, we looked at what can you learn even if HTTPS works exactly as it's supposed to. So you have a secure tunnel, the secure tunnel's in place, but the adversary is still watching everything that goes through the tunnel. So they can't see inside the tunnel, but they can see sort of the endpoints of the tunnel. They can see kind of the volume of information, different subdomains that are being loaded when a page gets loaded. And so we established that you can actually tell quite a bit about what a user's doing based on just, even if HTTPS is in place. Today we'll talk about breaking into the tunnel. And then later today, we'll also start talking about ending the tunnel at the adversary. So get the tunnel pointed at you, and then if you can get the tunnel pointed at you, then you can read everything that goes over the tunnel and modify it as well. Okay, so to break into the tunnel, what we're talking about is breaking the crypto, so the cryptography that's involved. And what do we mean to break the cryptography? Typically, the way cryptography works is that there's some key that the party has that you're doing cryptography with. So we'll focus mostly on the server's key, but the client will establish keys as well. And the goal of breaking in the tunnel is basically, if I can get that key, then I can get into the tunnel. Okay, so if I can get the key off the server, then I can get into the tunnel. Now, how all the crypto details work, that's like an entire course. So in 6.1.10, you'll learn about symmetric key encryption, you'll learn about MACs, you'll learn about signatures, you'll learn about Diffie-Hellman key exchange, and HTTPS uses all of those. It wraps it all up into a protocol. And so it's not really possible for me to teach you the cryptography itself. So what we'll do instead is we'll just sort of focus on the high level sort of things. So some ways of attacking is you can just try and get the key without attacking the crypto, and then in other cases we'll look at what you can do at the cryptographic level, but just at a high level to get across the sort of the principle of the attack rather than the details. Okay, so my sub-strategies here are, one is I'm just going to try and get the key. If I can get the server's key in particular, then I can break the tunnel. And the second thing I might do is I might try and break the crypto itself. So an attack on crypto assumes that you don't have the key. If you have a key, you don't have to break the crypto. You can just decrypt. But if you don't have the key, you shouldn't be able to break the crypto. But let's see if that actually is the case for HTTPS or not. Okay, so how do we find ways to get keys off of servers? So one thing we might turn to is something called side channel analysis. And this is something useful to know about in security in general. So this slide isn't about HTTPS exactly, it's about side channel analysis in general. But the idea of side channel analysis is when you have a security system, you make assumptions about how it's deployed, and you usually don't really concern yourself about the implementation details. So for example, in HTTPS, you have some crypto algorithms. They're running on a computer, that's fine. So they're going to run on the computer's going to compute the values. You don't really think about like what kind of computer is it or how's it computing the values and things like that. Side channel analysis will take that into consideration. So the adversary might say, well, the way that it's implemented actually matters. So I'll give you an example. Let's think about the time it takes to encrypt. Let's say that I can watch the wire. I see sort of messages that go in and then they get maybe decrypted and re-encrypted and sent out, something like that. And I can get a kind of estimate of how much time it takes to decrypt. Okay? Could that tell me something about the key that's being used to decrypt? All right? So if the encryption algorithm is math-based, say you have to add integers together or multiply or do an exponentiation, well, if the integers are really big, that's going to take a little longer. And if they're a little smaller, then it's not going to take as long. Okay? And so if your key is one of those integers that's you're doing math operations on, I might be able to tell the difference between someone using a key that's small and a key that's big just based on the amount of time that it takes. Okay? And so there's a lot of study about like every like little step in the algorithm, especially where you branch, like if the key bit is 0, you do this. If the key bit is 1, you do this. And there's some slight difference between them. And so anyway, there's a lot of work. Most of this is like kind of theoretical, like it works, like you can recover keys just by looking at time, but you need really sensitive clocks. And if the adversary's on the wire, like halfway across the country, it's probably not going to work. But in a lab setting where the adversary is sitting right beside your laptop, then they could pull out the key or key material based on different choices that the algorithm makes. Okay, so the one aspect of the algorithm, HTTPS algorithm, that was vulnerable was there was a mode that's no longer supported. It used an encryption scheme called RSA. RSA is one of the first public key encryption schemes you'll learn about in crypto. It was the original scheme. And RSA had this, anyways, there's this thing where you sort of pad the message at the end. And there were some vulnerabilities in the padding. And I won't go through the details of it. But basically what you could do is you could try to sort of tweak encrypted messages, and when they decrypted, the padding might catch whether there's an error or not, and based on whether there's an error or not, the person might give an error message really quickly, or they might wait a while because it happens to come out to a value that's padded correctly, but then the actual value itself is garbage. And so you could do subtle timing attacks to try and figure out which of the two was happening, and that was key dependent. Okay. Now, the good news is that today we've done two things to fix this. So the first thing is we got rid of algorithms that have these kinds of attacks to our knowledge. So this padding oracle RSA is no longer even an option in HTTPS. And the second thing we did is we rewrote the crypto libraries, especially the very popular implementations. OpenSSL would be an example of one. And what happens now is that every single operation is time independent. So if you do an encryption operation, it always takes the same amount of time. There's no optimization that's applied. So if there's shortcuts that you could take because, say, your key has a lot of zeros, and when you hit a 0 value, you can skip a couple steps. In OpenSSL, they'll do the step anyways. They won't skip it. Just so that the time difference between whether your next key bit is a 0 or your next key bit is a 1 is exactly the same. Okay, so it does extra work. It's the opposite of optimization, where everything is constant time. So it takes the same amount of time regardless of the key material. Okay, so that was to harden these libraries against time channel analysis. Now there's other kinds of side channel analysis that you can look at. So you can look at the time. You can look at, for example, power consumption. So there were some attacks on ATMs where what you would do is if you had access, like say the ATM was plugged into a wall and you could actually access it, what you could do is put a voltmeter, plug the ATM into the voltmeter, plug the voltmeter into the wall. It would take time measurements. And then when users typed in their PIN, what would happen is if you type a 1, it creates, I don't know the electrical details, but it creates some resistance or something. And so you could see it like on very sensitive power measures. So it would create a like kind of disturbance in the power consumption. But if you press the number 3 instead of the number 1, it would look slightly different. So if you were measuring the power consumption very slightly, the resistance of each key would be slightly different, and it would make a sort of fingerprintable pattern. And then you could read out people's keys just by looking at the sort of the voltage or the power consumption. Similar attack occurred on voting machines. In this case, they're electronic voting machines. So if you vote for Alice, you press the button beside Alice's name. If you vote for Bob, you press the button beside Bob's name. The same thing. The electrical engineering, the sort of analog circuits that are used. If you press the one button, it behaves slightly different at a very like low level, like millisecond level, than if you press the Bob button. In this case, what they were listening for was electromagnetic interference. And so you could actually stand outside of the polling place with a radio, and if someone presses a button, it would create a kind of pattern that you could detect with the radio outside. And you could differentiate between the different machines in the polling place and also which buttons. So you could tell whether someone's pressing the A button or the B button, depending on just looking at the interference that came off of it. You can use sound. I attended a talk when I was doing my PhD. It was from the S in RSA, so Adi Shamir, and he was giving a talk, and he was saying that he was sitting at his computer, and he had one of these like desktop computers, like the one down here, and desktop computers, especially maybe 10, 20 years ago, they were always like pretty noisy. Like there was a lot of like clicking, like kind of sounds, weird sounds that emanated from it, and those sounds have something to do with the computation that's being done, okay? But like tracing the source of the sound to the exact computation, you don't really know, but you could try to treat it like a black box. So what he did is he asked it to do RSA encryptions, and he would measure the sound, and he would use the same key over and over and over again, and then he would say, okay, that's kind of like what that key sounds like when it encrypts. Then he would try another key, and it would sound slightly different, and then you could feed it into like a machine learning algorithm or something like that and say, find the pattern, right? And so he was able to do it. And so, if you could basically put a microphone beside a computer, you could listen to it do an encryption, and then you could read out the key that was being used to encrypt just because it sounded different depending on the key itself. Now, I don't know how well that works on modern computers, and of course the adversary has to be right beside your computer with a sensitive microphone. They also have to know when the encryption starts and when the encryption stops. And so it's again, a kind of laboratory experiment, but the fact that you can do it is concerning. Another thing is we all have phones. Our phones have a gyroscope. What's a gyroscope? Yeah, so it senses the sort of the plane that the phone's on. Why do we have it? So if I'm watching Netflix and I hold my phone like this, it's showing me the screen in portrait mode. And then if I turn it like that, or if I have my camera and I turn it, then now it's in landscape mode, right? So the gyroscope is the thing that does it. You can also do things like a compass on a map, and there's different like applications of it. It turns out the gyroscope in your phone is actually very, very sensitive. So it can tell like small differences in it. It can tell the difference of. So what happens is when people type, they're sort of pressing their phone, they're kind of rocking the phone a little bit. And if you're pressing a key that's way over on the edge of the phone, you're going to rock the phone a little more than if you're pressing a key in the middle, okay? And so what you can do is you can, again, using machine learning, a lot of data, you could train a model that basically would learn what does the vibration look like when the person presses the letter A, as opposed to what does it look like when the person presses the letter D. And you could essentially read out someone's password, not 100%, but with like high probability, high accuracy, you could determine what they are if you had access to the gyroscope data. Who has access to the gyroscope data? Well, it could be any app that you install on your phone. So if that's a permission that's exposed by the operating system and apps can ask for that permission, you might have to approve it when you install the app, right? But once you approve it, then those apps have access to that data, and so they can read out what you're typing. Another type of side channel analysis is just visual. So like there's a lot of work on like reflections. So like say I'm sitting here, I'm looking at my laptop, you can't see the screen because you're behind it, but you can see my glasses and you can see the reflection of my screen in my glasses. So if you had a highly sensitive camera or a high definition camera, could you take a picture of me looking at my computer, go into like zoom in on my glasses and the reflection, and could you actually reverse out what I'm seeing on my screen? And so it turns out that you can do that like fairly effectively. And so in a lot of offices, for example, you might be in the office building across the street. You can point a camera at it. If there's a window and there's some sort of reflection on the window, if you can get the screen on any sort of reflection, then you could actually read out the contents of the screen, again, with high probability. Okay, so we consider all these like sort of side channel, meaning that you're sort of exploiting something that wasn't modeled for, right? So anyway, side channel analysis shows up a lot because the adversary doesn't care. Whether you modeled for something or you didn't model for it, the adversary doesn't care. They just want to attack your system. So if they can attack it through side channel, then they're going to attack it through side channel. They don't have to go through the front door of how you want them to attack the protocol. Okay, questions about side channel? Okay, next thing I'll talk about is a bug called Heartbleed. So Heartbleed was a vulnerability. It was a well-known vulnerability, like you could read about it in CBC News or whatever. This is sort of the way it worked. So the vulnerability was, actually it was on the server side, not on the client side, okay? So web servers may or may not have had the vulnerability. If they had the vulnerability, it was because they were using a particular software stack. So the vulnerability existed in a library called OpenSSL. OpenSSL is the default HTTPS library that you would use if the server you're running is called Apache. Apache is a Linux server. It's the most popular web server on the Linux, Unix open source side. Okay, rivaled by like Windows and other like closed source networking server like operating systems. And so if you had Apache and you turned on HTTPS and you didn't do anything different, you just accepted the default, you'd be running OpenSSL. And OpenSSL had a library called Heartbeat, and this was also turned on by default. Okay, so it's estimated that maybe 40 or 60% of servers on the internet had this configuration and are going to ultimately be vulnerable to this vulnerability. Okay, the Heartbeat protocol is sort of a weird protocol. It was something that was like in the code from the very beginning, and nobody really used it, and people kind of forgot it was there. And it wasn't also like studied or scrutinized very well. And the way it worked was it was sort of like a liveness test. So if you just wanted to check whether a server supported the protocol they were running, the library or something like that, what you could do is you could just send them some bytes on a special port, or I forget how you distinguish it, but you would distinguish the packet as being a Heartbeat packet. You would send it some bytes, and then the server would just repeat the bytes back to you. And if you got that repetition back, then you knew that it had enabled OpenSSL. Okay? And then for, I don't know, efficiency reasons or something, there was a second parameter, which is you could give it a bunch of bytes, and then you could say, don't send me all the bytes, just send me the first 5 bytes. Now, I don't know why you wouldn't just send the first 5 bytes if you only want the first five bytes. Like, why send more than you want back? But anyways, this was how it was coded up. So you would send a byte string. You would ask for the first 5 bytes back, and then it would echo it back, and then it would tell you that it was on. Okay? Now, this is pretty simple, but does anyone have a feeling of maybe something that might go wrong with this because it looks maybe like something that you've seen before? Okay, no problem. What if, for example, instead of saying, actually, I'll ask you some questions about it before. Instead of saying echo 5 bytes back, what if I echo back 10 bytes? Okay. What should happen is it should say, well, you only sent me 7 bytes. You want me to echo back 7 or 10. 10's more than 7, so I'm not, there's an error, right? I won't do that for you, okay? But the way it was coded is it didn't check that condition, okay? So what you could do is you could say, here's a string, echo back 1,000 bytes, okay? And it wouldn't throw an error. It would try to do that, okay? Now, I don't know what it's going to do, but it's going to try and honor it. It's not going to throw an error, okay? So it's going to send you back 1,000 bytes of something, okay? So what's your guess as to what happens in that case? So software is not going to throw an error. It's going to send you back 1,000 bytes of something. What's the something that it's going to send back? Say loud. I just can't hear it. So garbage from where? Okay, so it could draw random numbers out of the random number generator, so it won't do that in that case. That would be like sophisticated. It's going to do something simpler than that. So it could repeat the message. That would be a sensible thing again. Again, you would have to program it to behave that way. In this case, they didn't program it to do anything. They didn't expect that someone would ask that. Like just imagine it never even occurred to you that someone would ask for more bytes than they sent. Okay? So your program's just going to do what it's going to do. Yeah. Okay, and what does that mean, the next value? Okay, so it could wait for the next request, but it's going to do it right away. So I send A, B, C, D, E, F, G. It sends back 1,000. It can't wait for the next request. It's going to send me back something right away. So it is going to send the next value in a sense, but what's the next value? Where is that next value? What exactly is it? So it's going to send back basically the data that's sitting beside A, B, C, D, E, F, G. Okay? So what happens is when you send the request, because it knows it has to remember that string, what it does is it puts it in memory, and not right to the hard drive, it puts it in RAM. So RAM is like the working memory. Okay? Then when it echoes it back, basically what the code does is it says, I remember the address where I stored this in RAM. So I'm going to go there. I'm going to start reading the first byte, the second byte, the third byte. I'm going to go to 1,000 bytes. And when I'm done reading, then I'll send all of that across the wire. Okay? So it's basically whatever's sitting beside that value in RAM of the computer, that's going to get sent back along with it. Okay? Yeah. So what? Like, tell me more about what you mean, because you're onto something. So I didn't say that. I just said it was going to store whatever is beside it in RAM. Yep. Okay. All right. So then what will happen is it will, okay, so first off, how is RAM, you said the first request. So why is there nothing beside it if it's the first request? Let's start there. You're right, but why? Okay, so RAM works like a stack. You might have heard that term, right? So stack, it's like an elevator, I guess. So the first people in the elevator are the last people out, right? So stack is when the server starts up, it boots up for the first time, it starts writing stuff into memory. So it writes at the first address and it adds it and adds it. And then when it consumes something, like when it pulls this out of memory, it's done with it. It doesn't have to do it anymore. It doesn't have to see it anymore. So it moves the stack pointer down. And so the stack kind of grows and shrinks over time. Okay? So the stuff beside it in memory is going to be the stuff before it in the stack. So it's going to be the stuff that's already in memory that hasn't been erased yet. Okay? Now, if you hit it at the very start, right, like this machine just boot up, you would get whatever's in memory to start. And it's probably already full with stuff because by the time you launch the operating system, you launch OpenSSL, you take a network connection, you do the cryptography, you probably have enough stuff sitting there that like you're not going to run out. But if in theory you did, what it would do is it just wrap around to the end of RAM. And then it would pull at whatever's at the end of RAM. Yeah. And RAM is, what happens to RAM when you turn your computer off? Does it like zero it out? Like what happens? Okay, so it gets erased because it's like, it's not persistent data. So when you write to it, it's the electricity of your computer that's keeping the RAM contents intact. When you turn your computer off, all the electricity disappears, and so the RAM starts to, like the values start to dissipate, okay? It does happen slightly slowly over time. It's not an instant process. So there is an attack called a cold boot attack where you get someone's computer, you freeze the RAM, which slows down the process of them, like literally freeze it like with cold, something cold. It slows down the rate that it dissipates. You yank the RAM out of the computer, which cuts the power. You quickly put it in another computer, power it back up, and then you can recover the contents of RAM like pretty reliably. So cold boot attacks are like something that, anyways, that's another whole attack, has nothing to do with this. Okay, so the point is that, so we call this a buffer overread. So it's kind of related to a buffer overflow, but in this case, we're not writing data outside. So the buffer is sort of like the fact that this string is 7 bytes long, that's considered a buffer. It's a bunch of characters that has a certain length. And because we're reading beyond the end of it, we call it a buffer overread. And if we were writing beyond the end of it, it's called a buffer overflow, which is another type of attack as well. So generally, we want to check, anytime you read or write strings, you want to have like the length of the string, and you want to check that you don't go beyond the length of the string. Okay, it turns out for heartbeat, you could ask for different values here. You couldn't ask for an infinite amount of data, so there was an upper limit on it, but the upper limit was 64 kilobytes, which is a lot of data. Okay, so you could ask for up to 64 kilobytes, and so it would just send you back like basically the most recent data that was in RAM that hadn't been erased yet. Also, when you're done with stuff in RAM, you don't erase it. You just, the stack moves down, but the old stuff just sits there as well. So I can't remember if the read up in RAM or if it read down, but in any case, you're getting a bunch of stuff that's sitting on the server. Okay, what's the kind of data that would be sitting on a server, like an internet server in the server's RAM, that someone might even possibly care about? So stuff related to the service itself? What are other things that have to go into RAM at some point?
Yeah, the variables for the database or whatever.
Okay, so there could be there could be the different configuration variables, settings, stuff like that. Not caring too much about that yet. Okay, what if you send a password? You're going to log in. What does the server have to do? Well, it has to take your password, hash it, compare it to the database of passwords. So what it's going to do? Well, it has to put your password in RAM. Then it calls the crypto library. It hashes it. Then it has to pull in the library of the database of all the passwords. It has to put that in RAM, and then it's going to compare the two. Okay? So everything goes into RAM at some point. So someone's password that they just typed in because they connected recently to the website, that's the kind of thing that could be sitting in RAM that you might get. Okay?
Is it possible to echo something an amount bigger than the RAM size?
I don't know. So you could request up to 64 kilobytes. If the server had less than 64 kilobytes, say it had 32 KB RAM, I imagine it would just go in a cycle because that's how it would be programmed by default, but I'm not exactly sure. Yeah. And most servers are going to have way more than 64 KB RAM, yeah, even at the time of this attack. Okay, so passwords, usernames, cookie values, which are kind of like passwords. We'll talk about cookies a little bit later. Also just data. So like, for example, if people are uploading things or reading their emails, the server has to put it in RAM before they construct the HTML to send down to the user. So there's all this stuff that's just sitting in RAM. And every time you ask for this, the RAM contents will change, right? So this is an attack where you can just run it on a loop, and then you're sort of getting 64 kilobytes of sort of slices of RAM at different times, and then you can sift through it and try and pull out passwords, keys, and all of that type of stuff. Okay, so this attack was really bad. So it was very devastating because for about half of the web, you could just pull out people's usernames and passwords and things like that. Now, one thing that would be extra devastating is going back to HTTPS. When a server starts up for the first time, it has a secret key. And we'll talk a bit later where the tunnel ends, like what that key is used for. But it's going to use that key in every single connection. Okay? And this key is something that it keeps for about 2 years, and then 2 years later it might change the key or something like that. Okay? So if you got Google's long-term key, you could impersonate Google for about 2 years. Okay? Module the fact that they find out about it and try and do something about it, which is something else that we'll talk about called revocation. But anyways, the problem with the TLS key is it actually goes back to the earlier point, which is it's like the very first thing that's loaded into memory. So it's the very first thing when this OpenSSL opens, it grabs the key right away. Then the server gets busy with stuff, and all that stuff ends up usually more than 64 kilobytes deep into the stack. And so when you do this attack, you're never able to get that private key because it's past the reach of 64 kilobytes. Okay, you can't reach far enough back in time to grab it. So it was speculated that even though this was a bad attack, the adversary was only getting ephemeral information that would allow it to break connections that were happening at that moment, passwords that were happening at those moments, and things like that. They couldn't get this long-term key. Okay. Then security researchers, they read about this and they said, that sounds crazy, like there's got to be a way in order to get this key. And so they came up with an attack, and the attack was basically, they found vulnerabilities in servers unrelated to OpenSSL that would trigger a reset. So basically they would hit the server, they would send some malformed data packets or something like that. The server would crash. It would automatically reset to bring uptime back on. So a few seconds later, it would come back online. But now that it had just reset, it had completely wiped the contents of RAM. And so it was now fresh. And that key was, you were sitting very close to the key. So if you did Heartbleed on it immediately after a reboot, then you could get that key out. And so they were able to successfully demonstrate that you could steal the long-term signing keys as well. And so now this is an even bigger problem because all these companies, they have these keys and they're expecting the keys to be around for 2 years. And now it looks like anyone could have gotten those keys. You can't trust whether someone got those keys or not. So now you have to change your keys. Everyone has to change their keys. Okay. So anyway, there are stories too. This was just an interesting story. So this was a high school kid in Waterloo nearby. Actually, sorry, London, Ontario. And he read about Heartbleed. He was obsessed with computers. And so he thought, this is fun. Let me just try and see which websites I can find that are vulnerable. And so one of the websites that he tried was the Canada Revenue Agency, so the tax agency in Canada. And he was able to pull down social insurance numbers and different personal information. He didn't do anything with it. He was just playing around with it, trying to understand the attack. He wanted to see that it worked and see it with his own eyes. The problem for him is that CRA, even though they were vulnerable to it, they were also keeping server logs. So after the attack came out, maybe a day later or day two, it was all over the news, and they decided, they were updating it. One thing that would occur to them is, well, I wonder if anyone exploited this. So they'll go through their server logs and they'll look for anyone that called this Heartbleed protocol over OpenSSL during that window of time when it was vulnerable. And so they found his IP address. He didn't use Tor. And then he actually got charged criminally with it. So this is just a little lesson to you, right? If you hear about vulnerabilities and they sound cool, and even if you're just trying it out, you don't mean any harm, you're not going to harm anyone, it still is an offense. It's a legal offense. Okay. Now, in his case, he even though he pled guilty, added to a criminal record, they didn't give him like a harsh punishment. I forget what it was, but he kind of got a slap on the wrist and, don't do it again kind of thing. But anyways, I don't know why that slide's there. Maybe I'll delete it. Okay, questions about Heartbleed? Okay, so this is another way that you can get the key out. If you can get the key out, then you can break the tunnel. So that's how it relates to the attack tree. Okay, another thing that happens over HTTPS is HTTPS is kind of a tricky protocol because we saw last class there's a lot of different versions of it. There's SSL 3.0, 2.0, TLS 1.0, 1.1, 1.2, 1.3. There's a lot of computers out there in the world, and there are some people that don't upgrade their computer ever, right? They're still running, I don't know, Windows XP or something like that, and it's unpatched, okay? And so they're not going to have the latest and greatest in terms of crypto technologies. The other thing that HTTPS gave you is it gave you lots and lots of options about what encryption you want to use. These aren't chosen by the user. It's not like it's popping up like, do you want to use, I don't know, AES and Diffie-Hellman, or do you want to use RSA? It's not giving the user the choice, but your browser is negotiating with the server, and you're going sort of back and forth trying to figure out what's the best version of SSL that you both support. It's also the case that you might connect to an old website. So your browser might be the one that's up to date, and the website is the one that's not up to date. Okay? So for backward compatibility, browsers don't just implement the latest version, they also support all the past versions. Servers are the same way. Everyone tries to get the newest version and the strongest crypto algorithms possible. But sometimes because one of the clients isn't updated, that's not possible. Okay? So there's a negotiation that happens about what crypto that you want to use. All right? Now, what an adversary can do is notice that this negotiation has to happen before the tunnel is formed, right? This is a negotiation about what tunnel you're going to put in place. So the negotiation itself is not happening over the tunnel. If you already had a tunnel, then you don't have anything to negotiate, okay? So this is called the handshake protocol, but basically the handshake has to happen in plain text. And then once the handshake is done, then both parties turn on crypto. Now you have a tunnel, and then the rest of your interaction can go over the cryptography. So what that means is if there's an adversary on the wire, they can see everything that's happening during the handshake, and they can change anything that's happening during the handshake as well. Okay? So if I say, hey, I want to talk TLS 1.3 to Google, and Google supports TLS 1.3, but there's an adversary between me and Google, the adversary can change my message and say, hey, I'm an old client, I only support SSL 3.0. Then Google will receive that I only support SSL 3.0, and it will say, that's fine, I support it as well. I would prefer to use 1.3, but for backwards compatibility reasons, I support it. So I guess if that's the only thing you support, it's better than nothing at all, right? And so then it will say, okay, let's go ahead with SSL 3.0. Then the adversary in the middle flips the message and says, hi, I'm Google, I support 1.3. So I think I have a connection to Google that's over 1.3, but the adversary's in the middle, and so it's relaying stuff over SSL 3.0. If there's an attack on 3.0, it can exploit that attack, okay? Because it's going to happen on the data. And so anyways, so it can do other things too about like the crypto that's being used and things like that. So we call this a downgrade attack. So a downgrade attack is basically an adversary in the middle that's trying to downgrade your connection to something that's less than what you're asking for. And it turns out that TLS actually has a clever cryptographic solution to this problem. So what they do is they set up keys. They do the whole negotiation, we call it optimistically. So they're hoping there's not an adversary tampering with it, but they're not trusting that there isn't an adversary. So they do the whole thing, and then once both parties have their keys set and they have a secure tunnel, then they actually go back and they revisit it. And so what the client will do is they'll say, hey, we just had this negotiation, and what I heard you say is that you wanted to talk TLS 1.3 and you wanted to use this crypto cipher suite. And the server will say, yes, that is what I said, or it might say, no, that's not what I said at all, okay? And then in that case, you would tear down the connection and you would restart, okay? So what you do is, once you have the tunnel in place, you basically go backwards and you double check about whether the negotiation happened, okay? And the reason this worked is because even if you negotiated the worst possible tunnel possible, you still had what's called message integrity. So you couldn't change messages in the middle. At best, what an adversary could do is they could read the messages. So they could break the confidentiality, but not the integrity, even with the worst possible choices of every like version of the protocol in every cipher suite, okay? So that was lucky. Basically, what happened is they didn't let you negotiate details about the message integrity. They only let you negotiate details about the message confidentiality. And so because you always had integrity, you could always do this check after and see whether the handshake, you heard the right handshake or not. Okay, the next attack we'll talk about is something called crime. This is an acronym. And this is sort of a complicated attack. So again, I'm just going to try and give you the sort of flavor or the high-level principle behind it. But this setup of an attack, the way that it's sort of set up, you can break HTTPS, like there's 4 or 5 different attacks that all use the same setup, okay? So there's one called Beast, it's actually the original. There's one called Lucky 13, one called Poodle, one based on RC4 biases. And they all work kind of the same way, but the detail is a little different. There's one piece of the protocol that's a little bit different. But I think crime is probably the easiest to understand if you don't know anything about cryptography, okay? All right, so this attack is sort of, it's sort of elaborate. We're going to assume a little more than just we have a man in the middle that's intercepting traffic, okay? What I'm going to assume is that we have a man in the middle. They're looking at all the traffic. It's encrypted, so they're seeing it go back and forth. I'm also going to assume that they have some JavaScript, and the JavaScript is running on whatever website the user happens to be looking at, okay? So they're able to infect this website with some JavaScript, okay? Now, JavaScript is pretty powerful. It can do almost anything. So some things that it could do is it can open a connection to any URL that it wants to, okay? So let's say that it opens a URL to Gmail, all right? It can do that. It can create a little frame, and then whatever comes back from Gmail, it can display. But the JavaScript can't really read what comes back from Gmail for reasons that we'll get into later when we talk about the same origin policy. But what it can do is it can create that outbound connection. When it comes back, the browser takes it, but it says that because this came from a different place than the JavaScript, we're going to isolate it from each other. Okay, now let's say that you're logged into Gmail. Okay, so you get some bad JavaScript running. And the JavaScript says go open mail.google.com/inbox. What your browser will do is it will construct that packet. It will drop that packet on the wire and send it out. And if you're logged in, what that means is you have a special value called a cookie, and your browser is putting that cookie value into the packet. Okay, so you have a request that says give me my inbox, and the header of that packet is going to have a value which is your cookie value. And if the adversary is able to steal your cookie value, then the adversary can effectively log in as you. Okay, so they can, it's called session hijacking. They basically are you at that point. Okay, so what we're going to assume is that the adversary can create packets that have your cookie values embedded in them. We're going to assume that they just can't read the JavaScript. They can't read the cookie value out. Okay, it's going to a completely different website, so they can't just easily read it out. And we're also assuming that HTTPS is in place. So even though the adversary is in the middle, the cookie value goes across the wire, but it's inside the envelope that's being encrypted. Okay, it's not something that's on the outside of the envelope. Okay, so what the adversary sees is they see an encrypted version of the cookie. They see the ciphertext. Okay. But what the JavaScript can do is it can initiate, like, say, 1,000 requests. So they could see 1,000 versions of that encrypted cookie. Okay? Now, what we want to do is we want to try and break the encryption. And what we're going to do is we're not going to completely break the encryption. What we're going to ask ourselves is, could we just get a couple bytes of the stuff that's being encrypted? For example, if I could get a couple bytes of this cookie, maybe I could guess the rest, or maybe the cookie's short enough that I could get all the cookie, right? The cookie's just a small value. It's, whatever, 16 bytes, whereas it's not like I'm decrypting everything, like kilobytes and megabytes of information, okay? So is there a way to like with encryption, usually we like to think of encryption as all or nothing. It's like you either get all of the message or you get none of it. But is there a way that we could actually target specific bytes and try and remove those bytes? Okay, now the other assumption of crime is it doesn't actually work on normal HTTPS. So the HTTPS that we're running, this particular attack will not work on it. Some of these other ones that are based on the same principles, if your version of HTTPS is old enough, these attacks will work, okay? But this targeted HTTPS that use compression as well as encryption, okay? So there were some protocols that use compression. TLS has it like kind of supported, but it doesn't really turn it on usually. But there were some people like Twitter, for example, they had a competitor to HTTPS called Speedy. And so Speedy was something like if you went to Twitter and you used Chrome and Chrome supported Speedy and Twitter and Google supported it, then you would, instead of doing HTTPS, you would talk Speedy instead, okay? And it was kind of meant to be a modernized version of HTTPS that made a bunch of optimizations. And one of the things that they optimized was they turned on compression as well. So they would compress the data, then they would encrypt it. When you received it, you would decompress it, and then you would decrypt. Sorry, you would first decrypt it, then you would decompress it, and then you would look at the data itself. Okay. All right. Now, what can Mallory do? So what Mallory can do is she can, this request value here that's getting sent. She basically, see the purple bit, she controls that completely, okay? So she can choose what request, what web server you're going to, what URL you're going to. She can put in parameters into the request, whatever she wants, she can control. Once the request leaves the JavaScript, the browser is the one that puts the cookie value in. So she doesn't see the cookie, she doesn't control the cookie, she has no control over the cookie, okay? So think of it as a packet, and then there's a header. And so the packet itself is under the adversary's control. The header of the packet is not under their control, but they want to learn what's in the header, okay? Now the header and the packet get sandwiched together, okay? So they get put together. Then it's fed into a compression algorithm. Then it's fed into an encryption algorithm. Then it goes across the wire, and the adversary gets to see the end result of that, okay? So they get to see the compressed, encrypted version of it. And that's all they get to see itself, okay? All right, so this seems like if the encryption works fine, right, and she doesn't see the cookie value, seeing an encryption of the cookie value shouldn't help her at all, right? If she sees an encryption of it, it doesn't give her any information that she didn't know already, okay? The problem here, the thing that wasn't really thought through, is that the compression applies both to the cookie value and it applies to the request value equally, okay? Now, let's talk about compression for a second. Okay, so where is compression used? Can someone give me an example of something that you would see on the internet that would be compressed? Okay, so a large file. Anything else? Yeah. Okay, picture is a good example. Are pictures compressed or not? Yes, always? Sometimes. Okay, so it depends. What does it depend on? Okay, file format. So what's an example of a file format that's a compressed image? Yeah, so PNG, JPEG, GIF, that kind of thing. Anyone know an uncompressed file? Okay, I don't know that one. Bitmap's the one that usually is the traditional one. Yeah. SVG is maybe compressed or not, but it's not really a picture technically. It's more of a drawing, but yeah. And then, you can think about music. So like a WAV file would be uncompressed, an MP3 would be compressed, video, MP4, that kind of stuff would be compressed. AVI, I guess, is the uncompressed version for video. Okay. Now, let's say you have a picture. I'll give you two pictures. Okay. One picture is a picture of a landscape, and, the top 2/3 of the picture is the sky. The sky is blue, there's no clouds, that kind of thing, okay? And the other picture is a picture of a concert and the crowd, and there's lots of people, little people all over the image, and everyone's wearing different colors and things like that, okay? Which of those two pictures you think would compress better, if that's all you knew about it? Why the first one? Oh, the first one's the landscape with the blue sky.
Probably the blue sky.
Why?
Because it's simpler, less changes in color.
Okay, so it's simpler, there's less changes. And another way of saying the same thing is that the same pixels are repeated a lot. Okay, so that one shade of, like the blue is a gradient, so they'll be slightly different, but there's going to be a lot of repetition in that image. If you have an image that doesn't have a lot of repetition, then it's going to be hard to compress. Repetition's easy to compress because instead of saying ABC, 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 ABC 1,000 times, all I do is I tell you, write down ABC 1,000 times. And that's a lot shorter than actually, saying ABC 1,000 times, okay? So that's more or less how compression works. It's a little more sophisticated than that. But the only principle that you have to understand is that if you repeat the same values a lot, it compresses well. If you don't repeat the same values, then it's not going to compress well. The worst thing to compress would be a random image. If you have a perfectly random image, it probably doesn't even compress at all, okay? So you can't compress it. Okay. All right, so back to this attack. So the adversary controls the purple bit. The browser is putting in the black bit. They're getting compressed together, okay? And then the adversary is seeing the results of the encryption, okay? Now, remember from last class, let's say I have some data and it's 32 kilobytes long and I encrypt it. How long is the ciphertext, the encrypted form of it? Same, 32 kilobytes, okay? So it's like length preserving. There might be like very, very minor differences, like in terms of the exact bit length, but more or less encryption is length preserving, okay? All right, what if the adversary here, Mallory, what if Mallory starts putting guesses at this cookie value in the purple spot here? So let's say she just starts with the first 4 bytes. So she tries A. She puts it in the purple bit. It gets compressed together. It gets encrypted. Then she's able to see the compressed length. Okay? All right? If she's wrong about her guess, so for example, let's say that she put 093A. 093A is not anywhere in this string. There's no repetition. It's not going to compress well. If she's right, she happens to randomly guess a right value, then it's going to compress better because you don't have to repeat that thing. You just say, okay, put this value in these 2 spots, okay? Can she tell whether it compresses good or bad even though she's only looking at the ciphertext? She can, because compress well means shorter and compress bad means longer. And she can see the length because cryptography or encryption is length preserving. Does that make sense? Okay, so what she's going to do is she's just going to try every value, say the first 4 bits, and anytime she sees a shorter ciphertext come out, she's going to guess that those 4 bytes are somewhere in the cookie, okay? And so she's going to do that, and then once she gets a couple chunks that she thinks is in the cookie, she'll try different combinations in different areas. If she gets 2 bytes side by side that are correct, then it's going to get even shorter, okay? So she knows she's on the right path because when she's guessing, it's getting shorter and shorter and shorter, and then eventually she'll guess the cookie value, okay? So she's able to do this even though she didn't have access to the key. She just saw, the encrypted data, but what she had access to was, we call this an oracle, a compression oracle, because the oracle is taking the secret value. So the browser does know the secret value, and it's creating things that the adversary can see that are based on that secret value. because the adversary can see the length of the ciphertext, the length depends on this value here. If you change this value, the length changes because the compression changes. And so in a sense, it's leaking information about the contents of it because it's being used in compression and the amount of compression you're able to see. Okay? So it's a very subtle attack, right? And you're only able to get like partial information. Again, you can't just like rip through the ciphertext and decrypt everything. You're going to have to try 10,000 or more, guesses. And there's a good chance that your firewall or something's going to shut you down before you're able to open 10,000 outgoing connections with different guesses here. So there's a lot of reasons why maybe this is like a laboratory attack and it's not going to work in practice. But in principle, it does work. Okay? So you can break it. And there's versions of it or variants of it that are based on other kind of flaws in the cryptography that leak tiny, tiny bits of information. So there's things called initialization vectors. If you can predict them, it leaks information. There's padding schemes that tell you something about when you start modifying ciphertext bits. The padding's right or wrong, and you get to learn whether it's right or wrong, and you can exploit that. And then there was a stream cipher that was used it was supposed to be purely random, and it eventually was, computationally random. But at the very start, when it was when it would start get going, it wasn't random enough. So there was a bit of bias in whether the initial bits would favor 0 instead of 1 or something like that. I forget what the bias is. But anyways, if the cookie happened to sit in the packet where that bias was, then you could get some partial information. And if you do enough requests, then you could actually siphon out the value. Okay, so limitations, you need cross-site scripting because you have to get JavaScript running, and you have to be a man in the middle, so it's not a very realistic setting. You have to know where kind of the cookie is. You have to know the cookie's there. You don't want to have a lot of other stuff that's sitting beside it, so there's things like that. It's pretty slow. You can only steal like kind of bytes at a time, and so it's not the greatest attack. And it generates a lot of traffic because you have to do a lot of guesses. And the person, as soon as they browse away from this website or they close it, then the attack is over. If the network picks it up either on the client side or on the server side, it notices that there's an enormous amount of traffic, then it might try and do something about it as well. Okay, so it's not like a very super practical attack, but it works in theory. All right, questions about that attack? Okay, so if we kind of fill in the attack tree a bit more, what we want to do is we want to break the cryptography in the protocol itself. And to do that, we want to either get the key or we want to attack the protocol itself. So you could attack the crypto. You could attack the protocol, which is sort of like what bundles the crypto together, or you could attack the implementation of the protocol. Okay. So depending on where you are, there's a bunch of attacks here. Again, we didn't talk about all of these attacks. I'm just sort of including them for completeness. But of the ones that we did talk about, I gave you kind of the flavor of a version downgrade. So where you try and downgrade. By the way, the worst thing that you can downgrade to is no encryption. So there is an option for 0 encryption. You could also downgrade to a key that's 56 bits long. And I could break on my laptop in a couple seconds. Okay, so it's just like really, really small. Why were keys so small? Why were they ever part of SSL? So this is another story. When the internet first came out and SSL was first like introduced in 94, 95 kind of thing. At the time, encryption wasn't used anywhere else for like normal people. Normal people would never use encryption. The internet was the first place where people tried to use encryption, and like you and I and normal people would use it. The other place it was used was the military. And in the military, it was considered a secret. So we didn't talk about encryption. We didn't talk about how we did encryption and that type of stuff. And when cryptography as a field of research first came out in like the 70s and the 80s, most of the researchers were working out of the U.S. And so the U.S. government tried to shut down that whole field of study, and they tried to stop them from having meetings about cryptography and things like that. But the cryptographers did it anyways, and then eventually, the government backed off a bit. And then when the internet came out, they said, okay, this is really bad because anyone can download Netscape Navigator from anywhere in the world. It's not just for Americans, it's for anyone can do it. It's the internet, it's the World Wide Web. And so now we're going to put strong encryption in the hands of everybody. All right? We don't want that. Encryption's a military secret. There were actual laws that you couldn't export the algorithm of an encryption to another country. It was kind of like exporting a hand grenade or weapon or something like that. Okay? So what the government did is they said, okay, here's what we're going to let you do. We're going to let you make 2 versions of Netscape. One's going to have a super weak key that we can break, 56. It's still a bit of effort at that time to break it, but technically the government could get in if they wanted to. Netscape, you're allowed to give that browser to anyone in the world. Okay? But if people come to you and somehow prove that they're American, I don't know how that worked, then you can give them a different version of Netscape, and this has strong encryption in it. Okay? So what Netscape did is they said, we can't really figure out who's American and who's not, and we're kind of lazy, and I forget what the exact story is, but basically what they said is just forget the strong encryption. We'll release one version of the browser, we'll have weak encryption. Okay? And so that was the browser that everyone had at first. Then eventually they introduced the stronger ones. The government changed their policy around that time. So this would be the Clinton administration. So sometimes in the 90s, they relaxed that law. They got rid of it. And then all of a sudden you could export the Netscape, which had strong encryption in it. But because of legacy clients and legacy servers, that 56-bit encryption was always there. Right? You could always fall back to it. And so that's what attackers did for a long time, is they would try to just downgrade you to the weak encryption. But yeah, anyways. So that was one attack. RSA was the one that was based on time. Heartbleed, even though it was an attack on OpenSSL, it actually has nothing to do with SSL. That could have been a protocol that was in any web service that was offered by servers. Okay? The reason I put it in the attack tree isn't because it came out of OpenSSL. The reason was because you could pull SSL keys. It was one of the things that was sitting in RAM, and you could pull it out. Okay? If there's any other attack that would let you dump the contents of RAM of random web servers, then I would put that attack in as well. Okay? So the fact that it happened to be on OpenSSL is just sort of incidental. Beast, Lucky 13, Poodle, RC4 biases, they all work kind of the same as crime. It's about stealing small bytes of data. It's about sort of leaking information slowly over time. And then crime's the one that we talked about. Okay, any questions about these crypto attacks? Yeah.
Where is this Spear?
Spear, I didn't put in the tree. I think I mentioned it maybe. I thought I had it somewhere. Oh, back with downgrades. Anyways, it's sort of a combination. It's a downgrade attack. It's only a downgrade attack. I think it's an implementation. You could maybe put it under implementation and downgrades. I think. I don't remember exactly how it works, but I don't think it exploits any crypto details. I think it's strictly about downgrading you yeah. Other questions? Okay, so these attacks, if you're really into crypto and wanted to do like a course project or something like that on it, that's where you would do it. But other than that, we're not going to see these details. We're not going to see these attacks in details. Okay, next thing we're going to do is we're going to move from breaking the tunnel into trying to get the tunnel pointed at us. And this is kind of the largest category of attack. It's the one that we'll spend the most time on. However, the time is good for a break, so why don't we take a 10-minute break. We'll come back at 4, and then we'll go into getting the tunnel pointed at you. Okay, we'll get started again. Okay, so attack tree, recall, we're trying to break into the middle to see just to read what's going over the tunnel. We can look at the outside of the tunnel and try and infer the information, even though we're not trying to break it. We can try and break into the tunnel itself. And the final thing we can do is we can try and get the tunnel pointed at us. So the user thinks that they have a connection to Google, but what they actually have is a connection to us, and we're reading everything. And then we can forward it on to Google if we want, and whatever responses come back from Google, we can feed to the user, and the user doesn't know any different. Okay, so from the user perspective, the client, the browser or operating system, all your computer knows is that you're dropping packets into a tunnel, right? But you have no idea where the tunnel ends. Okay, does the tunnel end at the Wi-Fi router? Does the tunnel end at a completely different person? Does the tunnel end before it even leaves your computer? Right? These are all possibilities. And so what we'd like to do is we'd like to establish where the tunnel ends. We have to, more or less. Okay? All right, so where does the tunnel end? Does anyone know the answer before I show it? Okay, so this is the one piece we're going to pull crypto back into it, but then we're going to drop all crypto. Everything else is going to be not a crypto problem. The public key ends at what's called a public key. So a public key is part of cryptography. It's used to sign messages. It can be used to encrypt messages for someone. If you want to do encryption with other people, what you'll do is you'll create a public key. And because it's public, you can distribute it to everyone. You can say, this is my public key. And you have a corresponding private key. Okay, so the private key corresponds to the public key. And everyone knows your public key, and you use your private key, and then you can do communication. And so when I send messages in a tunnel, what you can think of is you're sending them to a public key. Okay, so, and they will go to that public key. You do have a secure tunnel to that public key, and no one else in the world that doesn't have the secret key associated with that public key is going to be able to read what's in the tunnel. Okay, so you have a tunnel to a public key. Okay, the problem is, how do you know anyone's public key? Okay, so if I want to connect to Concordia, I have to connect to Concordia's public key, right? I make my tunnel to Concordia's public key, but how do I know that Concordia's public key is their public key? How do I get it in the first place? Okay, so that's the problem that we're trying to solve. And if you can solve that problem, just have a list of, here's a bunch of people, and here's all their public keys, then there's nothing to do in this attack tree at all. Okay? This attack tree just like collapses at that node and it's all done. But we're going to talk about it the rest of today's class, and we're going to talk about it all of next class. Okay, so that should give you some indication that this isn't an easy problem, even though it sounds super easy to solve. Okay. All right, so tunnels go to public keys. What we want to know basically is, for example, let's use the idea of Concordia. What is Concordia's public key? Say this is Concordia's public key. How do I know whether it's public key or not? Okay, does anyone have any knowledge or guesses as to how?
It's signed by a trusted third party.
Okay, so what we could do is, okay, first off, why do we want to do that? What problem is that solving?
That's solving can this key be the one of Concordia? Because if you just ask the key, anyone can just send a random key, and you won't have any way to check it.
Okay, so let's start there. So let's say I just ask, I could go to Concordia and say, hey, what's your public key? Okay, so I do that. Now, can I do that over a tunnel? Can I ask Concordia's public key over a tunnel?
No.
No, why not?
Because you don't know where the tunnel, how to make the tunnel.
Okay, so the tunnel needs their public key. So if I don't know their key yet, then I can't ask for it over a tunnel. Okay, so I have to ask it for it over clear text. Once I have a key, then I can make a tunnel to that key, and then we can continue that conversation. Okay, if there's an adversary in the middle, and I say, hey, Concordia, what's your key? And that packet is going, from Concordia to me, the adversary can just swap it out for their own key. Now I get a packet back. I ask Concordia, what's your key? I get a packet back, but it has the adversary's key in it. Okay? So we're going to solve it the way that's suggested, but let's just denote this attack first. Okay? So the idea is that there's an adversary, they can switch this value out. And so when I just get this piece of information back, I still have no idea whether it's the right key or not. Okay? If it's the wrong key, if it's the adversary's key, and I create a tunnel to it, then I've created a tunnel to the adversary. Right? Okay. All right. So how do we solve this? So the suggestion is, what if we have somebody else vouch for the fact that this is correct? Okay. So we could go to a third party and say, hey, do you know Concordia's key? And the third party will say, I know what Concordia's key is. Or one thing that comes with public key in cryptography is you get something called a digital signature. So we could have that party basically sign a document that basically just says, here's Concordia, here's the key. There's a signature on this document, and there's a company like GlobalSign that signs this document. Okay? Attesting that this is Concordia's public key. All right? So we call this a certificate. You might have heard that term before. But a certificate is just, here's an entity, here's their public key, and somebody signed that information saying that that's true. Okay, so that's certificate. Now, there is more in a certificate than just the subject name and the public key. There's a lot of stuff. We'll see examples of certificates. You can look at a certificate anytime you want. So, just go to, like, say we go to Moodle, and then, not sure where they always change this, but let's see. So if you go to connection security details, it says that, you have an encrypted connection or tunnel to moodle.concordia.ca. It tells you a little bit about what that means, and then there's a show certificate. And so you can see that this is the thing that I was talking about. It's signed by GlobalSign, and somewhere in all the details of the certificate, there will be the public key. So it will be right here. And that may or may not be the actual key. I guess when I made these slides, it was actually real, but it's been changed since. Okay, so that's certificates. All right, this solves the problem. Any problem with this?
How can you check that the third party is actually can be trusted?
Okay. So that's one point. So do I trust GlobalSign? What if GlobalSign is lying about what Concordia's public key is? Okay, so that's true. Let's say I do trust GlobalSign. I think they're honest. They do a good job. What's another concern? How do I check a signature? What does that mean, check a signature? So this thing has a signature on it. What does that mean, I check the signature? What that means is I go get GlobalSign's public key, and I feed into an algorithm. Here's GlobalSign's public key. Here's the signature, and here's the thing that was signed, the plain text, the certificate. And is this signature valid or not? Okay, that's how digital signatures work. All right, where do I get GlobalSign's public key from? Okay, it's kind of the same problem, right? I wanted Concordia's public key. I had no idea what it was. So now I have this certificate, but to make sure it's signed right, I need GlobalSign's public key. So I'm back to square one. There's someone out there and I don't know what their public key is. Okay? And then the final problem with this is, how did GlobalSign figure out that that's Concordia's public key? Right? Like I didn't know what Concordia's public key is. That's why I'm working with GlobalSign. But how did GlobalSign figure it out? Okay? Yeah.
Maybe a verification, get the signature.
Okay. So we'll talk about that. So there will be a process that they use that we'll outline. Okay? All right. Now, the adversary here could change the public key to something else. Here, if you get a certificate, the adversary could say, hey, I'm GlobalSign. They could sign say they could change the key to their own key, and then they could sign it saying their global sign with their own key as well. Okay, so I need to know global sign's real key to know that it's actually being signed by global sign and not by the adversary. Okay, so the certificates are not at all a complete answer to the problem. So how do I get the public key of the certificate authority that signed the certificate? All right, and if I'm able to get their public key, like somehow I have method, call it method X, and I have method X and I can use it to figure out what global sign's public key is, then why don't I use method X to figure out what Concordia's public key is, right? And then I don't need global sign anymore, right? Whatever method I use to figure out this was right, I can figure out that this is right, okay? So this idea of having a third party sign seems like it doesn't help at all, right? Because now I'm back to the same problem. I still don't know what their key is. And if I have a way to figure out what their key is, then I have a way to figure out what Concordia's key is, and I don't need them, okay? So we shouldn't even have certificate authorities at all, you would think, okay? But we'll talk about why they exist. And then the second issue is how does the certificate authority know what the key is of the website, and why can't Alice use the same method to determine the key of the website? Okay, so we'll deal with these. And then the third issue that's not on the slides is related to the first one, which is how do I trust global sign in the first place? You know, who made global sign the authority of Concordia's public key? Okay, I flashed the answer, but if you didn't quite have a chance to read it, does anyone know how we solved this first issue? Or want to guess?
Maybe it's given by. Could be stored maybe.
Okay. So right terminology, but conceptually. Okay, so the answer is I go to the Apple store, I buy a brand new computer, MacBook Air, never turned it on, never connected to the internet, I boot it up for the first time. Global Sign's key is on that computer already.
Distributed by Windows.
Okay, it's distributed by Windows, it's distributed by Apple. Sometimes when you download a browser like Firefox, it will come with its own, they call it a key store. And so it's hard-coded in your computer or the software that you're using, and that's how you get it in the first place, okay? So I get global signs. I didn't learn it somehow. I didn't ask someone about it. Well, you're kind of asking Apple in an indirect way, but I get it on my computer, okay? So we call it a root certificate because it's stored on your computer. All right, now let's say I want to see global sign's root certificate. Yeah.
Where does root certificate? Where does it come from? Like, is there any standardization that they follow?
Okay, great question. All right, so this actually goes back to the other point, which is, so global sign, I bought this new computer, global sign's key is on my computer, right? Who decided that global sign was trustworthy and put it on my computer? Like Apple put it on the computer, but like what was the process behind the scenes for saying they are trusted or they aren't trusted? So the answer is yes, now there is a process. So there didn't used to be a process. It was just sort of like word of mouth. You sort of went and talked to Apple and then they would kind of put it on your computer, or Microsoft or whoever. But now it's become a problem. And so now browsers are very careful about who's allowed to have a root certificate and who's not allowed. And there is a process. There's a sort of kind of like an industry form called the CA browser form. And the decisions and recommendations, they're not standards because they're not law. Like no one is forcing you. You ultimately, Apple could do what they want to do, but they talk about it and make regulations that they self-regulate with. So they wouldn't have to strictly follow it, but they more or less agree to follow it. Yeah. And so if you look at like global sign, if it's on my computer as a Mac it's going to be on your Windows computer, it's going to be on your Android phone. More or less that if it's a root certificate on one operating system, it's going to be a root certificate on all operating systems, because they all kind of like come together and they kind of agree on the fact that global sign is trustworthy for this purpose. Does that make sense? Okay. Okay, let's say I want to see global signs certificate, so I can see it. So on a Mac, it's called keychain. And so there's system roots, and here's the root certificates. Now you can see a piece of this list. I said global signs on this list. How many other companies do you think are on this list? How many root certificates? Like, is global sign the only one? No? Are there like 10 of them?
Maybe like 5 or 6.
5 or 6?
It's big ones.
Okay. Good answer. Anyone strongly disagree with that? Okay, so that was certainly the vision for the web. So the web was that we would have 5, 6, maybe 10 certificate authorities. All right? Now what we ended up with is different. Okay? So here are the root certificates. So you can see global sign will be here somewhere. Now you can see they actually have they have about 10 different certificates themselves, but these are all from the same company, okay? But if you go through, you can see this list is pretty long. Okay, we're not talking 5 or 6 companies, we're talking like 50 companies here, all right? So that might surprise you. Why are there so many certificate authorities? And so the answer is sort of like, it has more to do with business reasons. Back in the earlier days of the web, browsers, anyone that wanted to be a certificate authority, they would sort of go to the browser, they would convince them, and it was hard for the browser to say, I'm going to let you be a certificate authority, but I'm not going to let you, okay? So what they ended up doing is they ended up adding a lot of people. And when you get one of these certificates that's signed, like Concordia goes to global sign, that is not free for Concordia. Okay, they're paying money to global sign to have this certificate. Okay, and it used to be, the prices have come down. Now there are options that will give you free certificates, but historically it wasn't free. And global sign didn't actually have to do that much information. Like, it was more or less a fully automated process, right? And so it was like costing them pennies to issue a certificate, right? Other than their reputation on the line, but they would charge $1,000 or $2,000, okay? So being a certificate authority was lucrative, and so lots of people wanted to do it, and the browsers and operating systems weren't saying no, or they had a hard time saying no, you can do it and you can't do it, and so they just sort of let everyone do it, and then all of a sudden it ballooned, and now we have 50 root certificates in our store. Now everyone's a little more concerned about it, and so it's a lot harder to become a certificate authority. We got rid of a bunch. But anyways, we're kind of in this situation where we have lots and lots, okay? Now, does it matter? Who cares? If there's, let's say this was 500 or 2,000, what difference does it make? Who cares how many certificate authorities there are?
It's a problem because any of them, they could, some of them could be malicious.
Okay, so let's say that 1 out of the 50 is malicious. How bad is that?
The website that they are authenticating basically would be attacked.
Okay, so different websites, like Concordia uses global sign, and Google maybe is their own certificate authority, and different websites have different certificate authorities. So if one of these certificate authorities goes rogue, let's say it's global sign, that's going to be a problem for Concordia because Concordia uses global sign, right? Is it a problem for Google if Google uses their own certificate authority? Okay, so very intuitively we would say no, it's probably not a problem, okay? But here's the issue. My browser, let's say I get a Google certificate and it's signed by global sign, even though Google themselves don't use global sign. Does my computer know that? It doesn't know that information, right? All it says is, was this certificate signed by something in this store? Okay? So even though it's unusual that I would get a certificate for Google that was signed by global sign who's not their CA, As far as my computer's concerned, it is signed by a certificate authority. The certificate authority is in the list of root certificate authorities, therefore it's valid. Okay? So the most important thing to remember is that any CA can sign a certificate for any website, and your browser will trust it. Okay? So back to this question, let's say one of these 50 is malicious. Okay? They can impersonate any website on the internet. All right? So if you're an adversary and you get access to one of these root certificates, you can man in the middle every single HTTPS connection. It doesn't matter whether that website uses that certificate authority or not. Your browser doesn't know it. Your browser will accept that certificate. So what I do is I just make up a certificate. I make up a key for Google that's my own key. I sign it with my fake CA, or my CA that's real CA, I guess, that's in the list. And then I send it to your computer. Your computer will accept it. It won't ask any questions. Okay, it's part of the protocol. Okay. Now there is a bit of nuance there. We'll get to it in a couple slides. But that's generally true, unless if you're a really big player, then maybe your computer knows a little bit more about what CAs you should be using. But for a site like Concordia, computers have no idea who Concordia CA should be. So they'll accept any certificate.
Did that happen?
Yes. So I'll give you some examples probably in the next slide. Yeah. Okay. Okay. The other thing too is if we look through this list, it's kind of small, but let me just read out a couple names. How many people have heard of DigiCert? Okay, Intrust, GeoTrust, GlobalSign we've heard of because we just saw it. GTS, Harata. Okay, so anyways, the point is that a lot of these companies, you may have heard of a couple of them, and there are some big names, but a lot of them are they're not companies you've ever heard of before. Okay, they're not Amazon and Google and Apple, right? They're some weird company. And so why do you trust them? Right? You don't even know who they are, and yet they can sign a certificate for any website at all. Okay? So the fact that there's 50 of them is kind of a problem. There's 50 companies that we've never heard of, and we're basically trusting them for all our secure tunnels. We're trusting all of them for all of our secure tunnels to every website. Sometimes in security, we call this weakest linked. So weakest link means, you have 50, and if you can attack the weakest one, then you get access to it. Okay? So some security isn't always that way. Say you have a door and there's 50 locks. If you can pick one of the 50 locks, you still have 49 locks. Okay? It doesn't help you. It does help you. It helps you marginally. Okay? Weakest link is the opposite. If there's 50 locks and you pick one of them, then you get access. And you can choose which of the 50 you want to pick, so you can pick the weakest one. Okay, now another thing that happens in certificates is it's usually not so simple as, Concordia gets a certificate and GlobalSign signs it. What usually happens is that Concordia will get a certificate that's signed by GlobalSign. GlobalSign will have a certificate that's signed by someone else, and then that someone else will be a root certificate in your store. Okay? So we call these certificate chains. So you have the site certificate on the end. You have some number of intermediary or subsidiary certificates. And then you have the root certificate, which is in your computer. No one has to sign your root No one has to sign your root certificate because it was put there by Apple. So you just trust it by default. Usually, if you looked at the format of the certificate, you would see that they just signed themselves. So it's called a self-signed certificate. But anyways, it's just put there, okay? And sometimes the intermediary is the same company, and sometimes it's different companies, okay? So let's go through the motivation. Why would a company, let's say GlobalSign owns both the intermediary and the root. So again, this is exactly the example that we see here. So GlobalSign, this RSA-OV SSL CA 2018, signed Moodle's certificate, and then this was signed by another certificate, which is Global. So we have this chain of certificates. Now, if GlobalSign is signing this certificate anyways in the end, why don't they just sign it with their root certificate? Any ideas as to why? Okay, so this has to do with operational security. So in order to sign a certificate, you need to get that private key. So let's say you're doing the signature on a computer or maybe an HSM, some sort of device. The private key is sitting in that device, okay? It's vulnerable. If the device is compromised or it gets compromised, then that key is gone. If you lose a root key, okay, then anyone can impersonate any website with your root key. And there's no easy way to change it either other than a software update. And everyone would have to install the software update, okay? So you don't want to lose access to your root key, all right? So what CAs will do is they'll literally keep their root keys like locked in a safe, in maybe like split up among multiple safes around the world on like different devices. And what they'll do is like maybe every 2 years, they'll come together, they'll do a big ceremony, and there'll be different people in the company that have access, and 3 of them have to put their fingerprints into like to get access to the room, and then they get it out. And what they do is in that that ceremony is they sign one of these intermediate certificates, and then they take that intermediate certificate and its private key out of that room. The root key goes back into storage. And then for the next 2 years, they'll use that key to sign everything else. If it gets lost, it at least, it has a 2-year kind of time window on it. And because it's a middle certificate, there is an option to revoke that certificate that we'll talk about like next class. But anyways, root certificates, by contrast, if you go into the root store, their expirations are usually 40 years away. So root certificates are meant to be secure for 40 years kind of thing. So the reason that they use a middle certificate is just because this is a 40-year certificate and this is like a 2-year certificate. And so they don't want to keep this. And every time like Concordia goes and says, I need a new certificate, they have to get the private key out in order to sign it. And if that's an online process, that means that private key is sitting on a server. So the key here is like a lot more vulnerable than the key here. Here, there's a lot of operational security around the key itself, okay? Now, sometimes the intermediates are actually different companies too. So Global Sign, you might go to Apple and say, I want to be a CA, and Apple says, no, we don't want you to be a CA. What you could do instead is you could go to Global Sign and say, hey, you're a CA, sign my certificate and make me a CA, and then now I can be a CA. Okay? So that's another option to become a CA. So you don't have to necessarily convince Microsoft or Apple. You could also convince someone that's already a root certificate to give you a CA certificate, and then you could issue certificates yourself. Okay? Yeah.
Why would a CA not use competition?
So usually they would get paid to do it. So I would go to them and say, I'm going to pay you. And then they'll be like, I'll make more money on that deal than I'll lose in business. So that's fine. Yeah. Or it could be more like political too. So like a government or something goes to them and says, make me a CA. Yeah. Okay. So we said there's about 50 companies that have root certificates. You can see them. They're on a list on my computer. How do I figure out how many intermediate certificates there are? So the problem with intermediate certificates is they're not on my computer. The root certificates are on my computer. They're in a file. The intermediate certificate, I never see it until I go to a website that uses it. So because I went to moodle.concordia.ca, I saw that this was the intermediate certificate, and that might be the first time I ever have seen that certificate in my life. Okay? So I don't see it until someone uses it. They cough up a chain that has it. Okay? So can I go and figure out how many intermediate certificates there are? The answer is kind of yes and no. So no, I strictly can't. No, if there's an intermediate certificate out there, it's signed something and I've never seen it, then I don't know whether it exists or not. Okay? The best thing I could do to try and figure out how many there are is go to every single website on the internet and write down the intermediate certificate that I see. Okay? Or I could require that intermediates are logged somewhere else, and I won't trust it unless if I see it in a log. So those approaches have been used to try and measure the number of intermediary certificates. So what you can do is you can't scan IPv6, it's too big, but you can scan IPv4. So the traditional IP addresses, that's like, 256 dot some 256.256.256, those numbers. You can try every single IP address. You can see what you can ask for HTTPS over it, and then if they respond, you write down their certificate authority that you see. So people did those measurement studies. They found that in addition to the 50 companies, there's about 200 companies that just have intermediaries that aren't in the root things themselves. And at the time, there were about 2 million websites that supported HTTPS. This number now is going to be huge. These numbers are a little out of date, but now almost every website supports HTTPS. Okay. There's also a log called certificate transparency. And so some browsers will only accept certificates if it's logged. And so in that case, you do have a list. You can see the list. The problem is that logging in CT is not turned on for every kind of certificate by every browser. So it's not yet at the stage where 100% of certificates need to be in CT. There's some rules about which ones have to be and which ones don't. So in a while, another couple years, we'll actually have a list. But for now, we have an incomplete list. Okay, so CA system, we also call it public key infrastructure, PKI. So PKI is just like Concordia's, you have Concordia and you have their public key. You bind that information together. It's called PKI. It's weakest linked. If you can breach one CA, you can issue a certificate for any site. And so someone asked, has this happened in real life? And so the first thing is, would you know that it happened? Let's say a CA was breached. It started issuing certificates, say for Google, right? But it is a CA that's in people's trust store. So they would go to Google, what they thought was Google. They would establish a tunnel that they thought was ending at Google. Their browser was telling them it ended at Google. Their browser was showing them the lock, or it was not saying it wasn't secure. Okay? And so, but it's actually an attack. How would you even figure out that that's an attack? Right? So it doesn't leave a fingerprint of an attack. Okay? So the problem is, for the longest time, we didn't know whether this attack occurred. We knew that in theory it could happen, but we had no way of knowing it. Then what Google said is, hey, we're sort of in a unique position. We now have a browser, Chrome, and it's very, very popular. And we also have a website, Google, and it's also very, very popular. And we have some like private stuff like Gmail and things like that people want private, that people like attackers would be interested in impersonating. Okay, so like targeting someone's Gmail might be like a standard thing that you might want to do. Okay, so what Google did very quietly, they didn't really say that they were doing it, is they figured out what keys they were using, or at least the certificate authorities that they were using. They hard-coded it into Chrome. So Chrome knew that if it ever went to a Google website, it knew what certificate to expect, or at least what certificate authority to expect. And if it ever saw something different, it wouldn't say anything to the user, but it would collect that information and it would phone home to Google with it. Okay? So they turned this feature on, and then I think it was like within a week, they noticed that there were CAs out there. One of them was DigiNotar, and then a little while later, there was one called Komodo, and they were issuing Google certificates, even though Google didn't use them as their CA. So Google basically caught them impersonating them. Then they started studying it more, and they grabbed users' browser data and stuff. At least people who checked the box that said allow you to send your data back to Google. And they figured out that they weren't just impersonating Google. They had Facebook certificates and other popular things at that time, different websites that were popular at that time. Then they went to Komodo and DigiNotar, and then DigiNotar did an investigation, and they realized that they were breached. And then in DigiNotar's case, they were actually kicked out then of the CA store. So then everyone removed their certificates. Company went bankrupt and they folded. Komodo, basically same vulnerability, same problem. The problem with Komodo is they were big. DigiNotar was like this little Dutch CA. They didn't have a lot of like websites, but Komodo was everywhere. And so they said, Komodo's too big to fail. If we revoke it, it's going to, there's going to be so many certificates that have to get revoked. It's going to be a mess. And so they sort of, scolded them, but then were allowed they were allowed to stay. And so to this day, if you look at this list, you'll see Komodo in the list. So it's kind of a double standard. Some people thought it was hypocritical to penalize one instead of the other, but anyways, that's more or less what happened. And so now you can expect that it's not just Google. So Chrome, then people said, oh, that's awesome if you're Google, right? But like, what about me? I'm not Google. I don't have a browser. Like, it's not really fair that Google's able to protect themselves, but I'm not allowed to. So then Google said, you know what, we'll give this feature to anyone. So if you write to us and go through this little procedure, you can give us what's called a preload, and we'll put it in Chrome alongside our preloads. And then people that visit your website, they'll check out your certificate authorities. Yeah. Okay. Okay, another point is that CAs are not necessarily politically neutral. So CAs are in different parts of the world. They're in different countries, and different countries have different laws, and the governments of different countries have the ability to interfere with companies to varying degrees depending on what country it's in. So some companies, so some CAs are actually government. So for example, in the US, the Department of Homeland Security, it had an intermediate certificate. No one really knew about it until they went through the whole web, and then they noticed that, oh, like some CA that's in the root store gave the government, the US government, a certificate authority. And by the way, if you want to be, let's say you're an adversary and you're able to get an intermediate certificate or a root certificate, it more or less gives you the same power. You can still sign any website. There's no real reason why you have to like be a root certificate to attack the system. You can also be an intermediate certificate. Okay, so some are government, strict government. Some seem aligned with government. And then there's some that are like companies that are independent of the government, but they have collaborated with the government in the past. So for example, there was a telecom company in Saudi Arabia. They had got caught installing malware on phones in the firmware of the phone. And so that happened like a couple years before. And then people were going through all these CAs and they noticed, oh, that same company has a root certificate. So then there was a big push to try and get them kicked out. But then I think ultimately they didn't get kicked out anyways. But there were people that were trying to have that happen. Okay, there's some news articles about that stuff. Okay, so let's go back to the two issues that we had with CA. So the first issue is, how does Alice know that the public, how do they know the public key of the certificate authority? So the answer is it's hard-coded in their computer. And then the other one we didn't really answer, but I'll answer it now, which is, why can't I use the same method? So I want to know Concordia's public key. And so I'm learning what Concordia's public key is because Global Sign signed it. And I know what Global Sign's public key is because it's in my computer. Why don't you just put Concordia's key in my computer, right? Then I don't have to use Global Sign at all, right? Okay. Yeah, exactly. Okay, so websites are changing all the time. So Concordia may not have existed when I bought my computer, right? They might be a new university and they just put their website up yesterday. Even if they've been around for 30 years or 50 years, their certificate may be changed over time. Maybe they just turned on HTTPS for the first time, so it's a new certificate. So the site certificates are changing all the time. And so they're dynamic, so we can't hard code them, sorry. But the root certificates are meant to be stable over time, okay? So maybe there's a new root CA that gets added every couple years or something like that. And usually when they're added, they also get another existing root certificate to sign them an intermediate certificate so that people who don't update their computer have access to the certificate both ways. But then they eventually get a root certificate as well. So one example of a project that's a relatively new CA is called Let's Encrypt. And so Let's Encrypt started as an academic project, and their goal was to give certificates for free. So instead of charging thousands of dollars for a certificate, they would give you a certificate for free. And so they eventually were given an intermediate certificate. And now I think, I could check it, I guess, but I think they have a root certificate as well. So like, for example, if you, right now, like a pretty popular way to host websites if you don't want dynamic content on your website is to use GitHub Pages. So if you have a static website, you just put it on GitHub, and then you can press a couple buttons, and GitHub will give you a website. And then you can have a custom domain, or it can be like your thing.getpages.com. And then if you want to turn on SSL, you just push a button again. And then GitHub will go, and they'll go to Let's Encrypt. They'll get a free certificate. They'll configure it all, and then the whole thing just works out of the box. So it's very easy to turn on HTTPS. Okay, so let's move on to the second question. Global Sign somehow figured out what Concordia's public key was, right? So how did that happen? How were they able to figure it out? I couldn't figure it out. That's why I had to use Global Sign. So how did they figure it out? And if they have a method for figuring it out, why don't I just use that method? Again, I don't need to use Global Sign anymore. Yeah.
Maybe they asked Concordia to make the verification process for them to get the signature.
Okay, so let's try and think that through a bit. So Concordia goes to Global Sign and says, hey, I'm Concordia. This is my public key. I want you to sign my certificate. The CA says, okay, we're going to do a verification process. What would that look like?
Maybe like since it's related to the host, using the DNS record.
Okay, so one thing that's a great idea. So one thing we could do is we could try to like say, okay, if you're Concordia, then you control concordia.ca. So why don't you modify your DNS record and say, put your public key in your DNS record, and then we'll know it's you. Okay, so that is more or less one method that could be used. Anyone have any ideas about any other methods? Okay, while we're on that point, let's say that that was the process. So Concordia puts their public key in their DNS record. The CA pulls the public key out of the DNS record, and then they sign the certificate. Okay. Now let's think about the second thing. Why can't I'm getting Concordia's DNS anyways, right? I need their IP address because I want to go to there. So if their key is just sitting in their DNS, why do I need Global Sign or a certificate? Why don't I just pull their key out of DNS and then use it? Okay, that is a very important question. Okay, that's a question that we'll circle back to. And the answer is sort of like you could do that. Okay, and there are people that in the future, in 5 years down the line, they want that to be the process. They want to completely get rid of Global Sign and just have everyone's key sitting in DNS, and that's how you figure out what people's keys are. Okay, so keep that in mind. It's one of the last things we'll talk about in this little segment. But okay, now there's two kinds of certificates. At a high level, you can think of a certificate's going to bind a public key to, say, Concordia University. But what does it mean to be Concordia University? Does it mean that you're, the university that's in Montreal as opposed to the other Concordia that's in Edmonton and the other Concordia that's in the US? Okay, is that what it means to be Concordia? Another thing about Concordia, the thing that the reason why certificates come up is because you're going to Concordia's website. Okay, so you're going to concordia.ca. Okay, so that's another kind of part of, like, I want to tunnel to concordia.ca, right? And then I want concordia.ca to be the website of Concordia, the University of Montreal. So those are almost like two separate pieces of information. Okay, and so in a certificate, do we try to figure out that this key belongs to concordia.ca, or do we try and figure out that this key belongs to Concordia, the University of Montreal? Or both, all right? And so the original vision for the internet was that you would try to figure out it belongs to Concordia, the University of Montreal, okay? The problem with this is you have to, well, we'll talk about the process in a second. So that's a traditional style certificate. Then there was a switch, and we started issuing certificates that would only bind a key to a domain name. It wouldn't bind it to actually the identity itself. And we'll talk in a second about why that switch happened. And then the idea of a traditional certificate kind of came back, and they called it an extended validation certificate or an EV certificate. Okay, and so today there are these two kinds of certificates. There's also something that's kind of in between called an OV certificate, which is, for our purposes, we'll just lump it in with an EV certificate. And if you were really paying close attention, you will see that global sign RSA OV, there's that term OV in this here. That's a reference to the type of certificate it is. But okay. So let's start with the EV certificates, or the certificates where we try and figure out that it is Concordia, the university. This is like an in-person process, okay? So it would be a phone call between the CA and Concordia. You know, they might want to see documents. Maybe it's a like in-person visit where someone shows up, they show an identity card or something like that that proves that they are IT at Concordia or something like that. This is not like an automated, it's not machines talking to machines, it's an in-person process, okay? There's business documents. The business has to be government registered. The certificate will pull the details like the address of Concordia out of the government records and all of that kind of thing, okay? These certificates, as you can imagine, they're kind of slow. So it might take you 2-3 days. It might take you 2 weeks in order to get one of these certificates because it has to be validated. It's expensive because you're paying for humans on both sides, you know, to supply the information and someone else to validate the information. But it's pretty secure because they're going through, they're checking everything. It's good. The one attack that's still possible is social engineering. So there is an example of someone that worked at Microsoft and got fired, but then he was mad, so he went and got a certificate for Microsoft because he still had his employee card, and the CA was like, okay, it still looks like you work at Microsoft, and so they were able, or they decided to give it to him. Anyways, in that case, it wasn't actually for HTTPS, it was for signing code, like for if you write an application and then you want to have it signed by Microsoft. So it was for a slightly different purpose, but the PKI side of it was the same. So there is social engineering where you could try and pretend to be someone that you're not, but other than that, it's going to be a pretty secure process, okay? Now, there's one big problem with this. The big problem is, besides the expense, is certificates only last a certain amount of time, okay? So usually you get a certificate. Now it's standard that they might be a year or 2 years at most, okay? So I'll get a certificate. It lasts a year. That's great. I start my e-commerce business. I'm making $1 million every day. People are buying stuff on my website. Everything's good. All right. And then one day I wake up and I have a ton of emails from support saying, when we go to your website, it doesn't work. Our browser is giving us an error. And then some people like send a screenshot and the error says certificate expired. And I'm like, oh no, I forgot to renew my certificate. Okay, I had, it had an expiration date, and before the expiration date, I should have got a new certificate. I just totally forgot about it. Okay, now I have to go through this process again, and it's going to take 3 days, and I'm losing $1 million every day. All right, so people said that's crazy. You can't do that. People forget all the time, and so we need something that's faster. Ideally, I'd like it to be automatic, like just my computer talks to your computer, and then it's done. So that's how Let's Encrypt works. It's just ping, 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 done. Okay. So that's what I want, is some sort of fully automated process. This is just about the VeriSign certificate, the Microsoft person who was able to steal it. Oh, another thing too, before I turn to the fully automated one, if you want to tell the difference between an EV certificate and not, there was a time period where they would try and show you the difference, but nobody understood what it meant, and so all browsers got rid of it. But just for your interest, what they would do is they used to have like green as an indication. So for example, this is Safari, which I use the most. So you would have a lock, and it would be green as opposed to gray. So if it was gray, it was just a domain validated, and if it was green, it was EV or OV. And then what they would do is they'd also write the name of the company, the business name. So it'd say like Concordia University or Twitter Inc. or something like that here, as well as having the URL itself. So that's, for a while they decided that it was important for users to, they wanted to create an ecosystem where users liked EV certificates better, and then it would force everyone to use EV certificates, and then the web would be more secure. But instead, people had no idea whether it was green or gray. They didn't care. They didn't know what it meant. And so everyone just used gray anyways because it was cheaper, and then eventually they got rid of it. Yeah. So they're still used, they're just not distinguished. Yeah. Okay, So then we said, okay, can we do this in a fully automated way, machine to machine? And so the thinking was, if it's machine to machine, my machine as a CA has no idea what Concordia University is. It doesn't know about Montreal. All it knows is like internet stuff. It knows about IP addresses and HTTP, and it can go get websites and things like that. It can go to DNS and get stuff, but it doesn't know anything about like Concordia or Montreal or addresses or things like that, okay? So let's just completely forget about even trying to put those details into a certificate and have it like authenticated. What we're going to do is we're going to try and make a lighter weight certificate that just says this public key belongs to whoever's running concordia.ca. I don't know if that's Concordia University in Montreal. I don't know if it's in Edmonton. I don't know if it's an adversary that says that they went and registered concordia.ca. But whoever is running that web server, this is actually their key. Okay? So that's all these certificates try to establish. And then CA said that we can probably figure out in an automated way. So they had different ideas of how to do it. So one problem with this, though, is that if you go to the URL and it's not who you think it is, like you go to Google with 3 O's, and you think that's Google, the company in Mountain View, you might still see a certificate, there might still be a lock, right? But it doesn't mean anything about it being Google, the company you think it is, okay? So the lock kind of has a different meaning now. What the lock just means is you have a secure tunnel, and it's ending at the person who controls the URL that you're visiting, and that's all it means, okay? It doesn't mean they are trustworthy. It doesn't mean that they are the company that you think they are. It doesn't mean anything. It just means that your tunnel is ending at the same person that controls this domain. Okay, so there's 3 ways to do this. There's the email way I'll explain first. There's a way that you can use APIs or HTTP. Let's Encrypt uses this. And then there's the DNS suggestion that was mentioned already. All 3 of them are very, very similar. So I'll just explain the email one, and then the other 2 are more or less the same thing. Okay, so this is how email works. I go to a CA like Global Sign, and I say, I'm Concordia. And Global Sign says, okay, I have no idea whether you're Concordia or you're Jeremy Clark pretending to be Concordia. Okay? So I'm going to try and figure out whether you're Concordia or not. So here's what I'm going to do. I'm going to make up a secret password or like a number, a random number, challenge value. I'm going to email it to admin@concordia.ca. Okay? If you're really Concordia, you're going to go into that email address, you're going to copy and paste that value, and you're going to put it in the web form and send it back to me. And if you can echo that value back to me in the web form, then I'm going to believe that you're Concordia, and I will sign your certificate, and then we're done. Okay? If you're not able to do that, then that's fine. Then I just won't sign it, and I'll just ignore you until you can do it. Okay? So that's the process of it. Looking at this process, thinking like a security person, and you want to attack this somehow. You want to get a certificate even though you're not concordia.ca. Where do you think you might try to attack this protocol? Yeah. Okay, so whose mail server? Okay, so the domain or Concordia in this case? Yeah. So that email is sitting on the mail server, right? And the password's sitting in that email. If someone has physical access to that server, then they can get that email. Okay? So it could be an IT person, it could be someone impersonating an IT person, it could be someone that just walked by and the server room was not locked, or they picked the lock. I don't know, somehow they get access to it. They're able to get that, and now they have a certificate and they can sign for Concordia. Okay, so that's one way. Do you need physical access to get that email off the server? Can you get? Okay, so normally like emails you can download through some protocol. So like IMAP or POP would be the 2 protocols. If you download, you all have Concordia email addresses. What does Concordia need from you in order for you to log into your email? Username, password? Credential, yeah. So username, password, that's it. Maybe 2-factor, but I don't know if that's even turned on. I guess it is for Outlook, but not for our engineering specific one, but you need a VPN to get the engineering one. Anyways, okay, so let's say I get access to it. I guess your password, I install a keystroke logger, something like that. If I get that for the admin account, right, then I can log in and just download that email. Okay, so even though we're using, HTTPS is about encrypted tunnels, we're using keys, really strong encryption. If I can just get the password for one email account, I can defeat all of it. So even though we're trying to use strong encryption, it actually, like, the security is kind of falling back on things like username and passwords. Any other ideas? Okay, let's say I'm in the middle. So I don't have access to the mail server, but I'm in the middle and that email message goes by. Is email encrypted? Okay, yes. Who thinks yes? Who thinks no? Okay, if you think yes, put your hand up. Email. You send an email, someone's on the wire. Is it encrypted? Okay, so yes, maybe 3 yeses. How many people think no? Okay, well, I'll answer the question, but who thinks no besides you? Okay, and so 3 yeses, 2 nos, and lots of don't knows. Okay, the answer, it's actually sort of in the middle, but it might as well not be encrypted, is the end story. So email is not what we would call end-to-end encrypted. So what we would like is I encrypt it as the sender, you get the email and it's now on your device and you decrypt it, and anyone in the middle can't read it, okay? We don't have a secure tunnel for email. We do have it, the protocols exist, but just nobody uses them. So the 2 that exist are PGP. So that's something that's open source that you could use if you wanted. That would give you encrypted email. Or there's a sort of corporate version called SMIME. And then there's some other stuff too, like Proton Mail. And there's a few things that have, like, if you're internally emailing, like I'm at Proton Mail and I'm emailing someone else at Proton Mail, then it will be encrypted. But if I email Gmail from Proton Mail, then there isn't encryption. Mail servers will do what's called link-to-link encryption. So they'll encrypt it for the next hop, and then that hop will encrypt it for the next hop. The problem is, how do they figure out the key of the next hop? There is no PKI for email. So there's no certificates and certificate authorities and stuff like that. And so the way email works is that you just ask the server, what's your key? The server tells you their key and you believe it. If there's an adversary on the wire, then you believe the wrong key. You get the adversary's key. If the adversary is not on the wire the first time, then you get their right key. And because you have their right key, then all subsequent encryption will be fine until it expires, okay? So we call that, again, that's called trust on first use, or we call it optimistic encryption, where you ask for a key and you hope that it's the right one. And if you get the right one, then everything's good. But if you get the wrong one, then everything's bad. Okay, so if there's an adversary in the middle and they're able to break the opportunistic encryption, then they're able to read that email. There's no encryption on it, or there's not encryption that locks the adversary out of it. Then they just read the code out and then they can get the certificate itself. Okay, we could attack the client, same thing. We could try and get the key out of that's sort of covered already. Any other ideas? We could try and guess the code. Okay, so the web form, we could just submit a bunch of random codes. That may or may not work. It depends on whether the code is long and random. And so the suggestion would be that it's a long and random code. Okay, I have one other idea. How many people use Gmail? Okay, a bunch of people. What's your Gmail address? You don't have to say exactly what it is, but is that something that Gmail gave to you, or is it something you chose? You chose it, okay. So what if I go register admin.google.com and admin@gmail.com and no one happens to have registered that already? Then I get that email address. Now CAs are sending certificate information to that email address, okay? So another thing, a sort of hidden assumption here, is that Concordia has to know enough to know that they don't give admin@Concordia out to anyone, okay? That's their certificate itself, okay? That's their email. It's private use, only ITs can use it as well, okay? Now, is that common knowledge? Does everybody know that you shouldn't hand out the special email admin? Okay, so no, maybe yes, maybe no. Probably for admin, it is. Are there CAs that would send it to any other email address? Okay, why admin? Like I chose that specifically, so that is the specific email that's used. But like, why is that? Like, what does admin mean? Okay, admin is short for administrator. Okay, so people are supposed to realize that is meant to be only for administrators, which are IT experts. I'll ask a really stupid question. The word administrator, what language is that in? English. Does every country speak English? Okay. Do CAs exist in non-English speaking countries?
Yeah.
Are there CAs outside of Canada and the US? Yeah, absolutely. Okay. Do you think that maybe in those countries, those CAs might not use the word administrator? They might use whatever administrator the equivalent would be in their language? Okay. Now, if I'm in the US, like Concordia, can I go to a CA in somewhere else in the world that speaks a different language and get a certificate from them? I still can try, right? And so not only does Concordia have to keep admin at domain, they have to keep every like language version of admin, every translation of admin in every language. And then it's not even just the word admin. So there's other like terms like hostmaster. That's another like sort of reserved term. And so you have to know like what are all these reserved terms itself, okay? And then it just takes one CA to do something weird. So for example, there were a CA that would send it to SSL certificates at domain dot whatever, all right? And it was the only CA in the world. It was one of the 2,000 CAs. It happened to use SSL certificates. It wasn't well known that the CA was doing it. Somebody noticed it and they said, oh, that's weird. This CA is willing to do verification with this address. They went over to Hotmail, Microsoft's version of Gmail, now called LiveMail, I guess. And they said, I wonder if anyone's registered SSL certificates. And no one had. So they registered it. They asked for a certificate. They sent the certificate. Because the domain they were asking for was at live.com, SSL certificates at live.com, they got a certificate for all of live.com. Okay? Live.com is Microsoft's like whole thing, right? Like not only just their email, they have like tons and tons of services. Okay? So they could impersonate live.com as a man in the middle for anyone that wanted to connect to any resource at live.com, they could impersonate. Now the person was a security researcher, so they did it as a proof of concept, and then they disclosed it. And they even set the certificate up so that it wouldn't be valid. I forget why. They put something in it that would make it invalid anyways, but they just proved that it could be done. Then people got mad at the CA and said you shouldn't use SSL certificates as a domain name. No one knew that like we were supposed to save that domain name. But still, there isn't like a standard list of names, but people have assembled them. I have that in a slide. Okay, so let's go through these sort of one by one. So I could try and get remote or physical access to the mail server. Then I get a copy of the email, and then I can read it. I can guess or steal the password for admin.domain.ca. I can intercept the email because email uses, so it's called SMTP, so that's Simple Message Transfer Protocol. Some people think S stands for secure, but it means simple. And it's opportunistic, meaning that it's link to link and trust on first use, all those things. I could try and guess the secret value, but if it's long and random, that's a vulnerability that we can exclude. If it's webmail, I could register admin at domain or some other special email address that a CA might use. So this is an example of the story I told you about the security researcher who got Microsoft research for live.com. And they did it because they were able to register SSL certificates at live.com at LiveMail, or what was used to be called Hotmail. This is a list of some of the things that you're supposed to set aside. So admin is one of them, but you should set aside abuse, administrator, hostmaster, info, and the list goes on. And then some other people said, oh, that list isn't very good. We have an even better list. And this list has 1,250 words that you're supposed to keep set aside, just because there might be some CA or some other process that expects that to be an administrator account as opposed to a normal user account. Another thing we didn't talk about is, okay, so I send an email to concordia.ca. So I'm the CA, I drop that email on the wire, and it finds its way to Concordia's mail server. How do I know where that email goes? How do I direct it? Okay, so the answer is I go to DNS. I go to DNS and I say, I'm sending mail to concordia.ca, and I need the IP address of the mail server. I don't want to visit the website, I want the mail server address. So in your DNS record, you can have different IP addresses. You can say, if it's a web request, send it to this address. If it's mail, send it to this other address. So the mail record's called MX record. And so if you're somehow able to change the MX record on DNS, or at least the CA's view of DNS, then that email is going to go to the wrong address. Okay? How could you change that DNS? There's different ways of attacking DNS, like poisoning attacks and things like that. You could guess the password that's used to register the DNS. So Concordia will have a username password set up for whoever their domain registrar is, and then you could try and break into that account. You could call up, say they use GoDaddy, you could call up GoDaddy and say, hi, I'm concordia.ca, I'm having a problem, can you help me trouble fix it? And then somehow get the password out. So later when we talk about social engineering, I'll show you someone that did that exact attack. Not for the purposes of getting a certificate, it was for something else, but they did that attack where they attacked it via social engineering on DNS. Okay, and then quickly, there's two variants. So one is, instead of sending an email, what you can do is, as a CA, you can say, if you own the domain, put a text file at this location on your domain, okay? And then we'll go fetch it, and if it has a copy of your key, then we'll believe that it's actually your key, okay? Now, the problem here is it suffers sort of from the same problems. The first is the CA has to fetch this over HTTP. Why? Why can't they use HTTPS? Well, the reason we're doing this in the first place is because we want a certificate, and we want a certificate to be able to do HTTPS. That implies we don't have a certificate already, okay? So if we required HTTPS, then they would already have a certificate. So then we'd have a chicken and egg problem where you can't get a certificate without already having a certificate, okay? So we have to fetch this over HTTP because we can't assume they already have a certificate. That's why they're asking for a certificate. So anyone in the middle could grab that value or change that value. So it's kind of like an email that goes across in clear text. This request and response also goes across clear text. And just like with email, you can, like with webmail, you can register your own email address. There's other things like, web hosts, tools, and things like that that let you set up a web page. And if you set up a web page, sometimes you can choose where you want it located. And so if you're able to choose to put a file here, then you would be able to compromise this process. And then everything else, man in the middle, DNS, you could attack the DNS record for this, get the IP pointed at yourself. You could try and attack the web host computer that's serving this website up, break into the password, get physical access. Very, very similar. And then DNS would be, it's actually even better than these ones because in DNS you just have that DNS threat. So you go, basically you put your key in another record called TXT where you can just store plain text. So you put your key in TXT, and then that's it. The problem with DNS is it's not over encrypted channels by default. So we talked about this, I think, twice already. So when you go to DNS, you get back a response. But if there's an adversary in the middle, they can change that response. And so if you ask for someone's key from their DNS record, and there's an adversary between you and the DNS server, then they can just change the key to their own, and then you don't get security, okay? Now, CAs will do this because they trust their DNS. They usually run their DNS themselves. And there are protocols like DNSSEC that give you signed DNS records. And so a CA may say, we're going to use DNSSEC just for this purpose, but then we don't have to use DNS everywhere, okay? So that also kind of answers the question of why can't users just do this themselves? So they could if we had DNSSEC, then everyone could just put their public key in DNS, and then we wouldn't need HTTPS, the whole CA public infrastructure. So that process is called DANE. The problem is we don't have wide adoption of DNSSEC. If we had wide adoption, then we could actually get rid of CAs completely and just rely on DNS for figuring out what public key belongs at least to what domain. Okay, questions about any of that? Okay, we're running out of time, so we'll put a pin in it here, and then we'll pick this up next week, and we'll talk about other problems with the whole PKI on the web.